All right, this is going to be a walkthrough of a one-sample t-test. So over here on the left, your stats teacher experimented with a new testing format, and he wants to determine if it helped to improve his students' test scores. Last year, the average was 69%. Propose an appropriate one-sample t-test and use Excel to test your claim. So over here, we have all the scores. So there are 30 different test scores here, with an average of 72.3, sample standard deviation of 8.5. So the null hypothesis that we're working with is that that the test average is actually 69%. Right? So now we're going to presume that this is coming from some random sample of a larger population of exam scores. And let's presume that we only know this small sample of 30 scores. What we would like to show is that the test average is greater than 69%. So in symbols, what we're looking at here, so for the null hypothesis, that's the mean equals 69 versus the alternative, the mean is greater than 69. All right, so based on that information, the sampling distribution is centered at a 69% test average. Now, the standard deviation actually shouldn't be called standard deviation in this case. We don't have the population standard deviation, so that forces us to use t, and it forces us to call this measure of spread standard error, not standard deviation. Okay, so we get that by going to our handy little formula sheet, which is right here. So we are measuring a single mean, so our standard error formula will be given by this guy. So our sample standard deviation is going to be replaced right here, divided by square root of sample size. So here we go. So this is equal to our sample standard deviation over square root of sample size. There's our standard error for the sampling distribution. Now, the hypothesis test itself has to use the t-distribution. We are using the t-distribution not because of the sample size, but since we don't know the population standard deviation. Right? If we knew the population standard deviation, we would be using normal. Since we don't, we're going to use t. There's also some kind of hand-wavy arguments about the sample size itself. Forget them. This is the reason you're using the t-distribution. So the t-score, if we go back to our handy little formula sheet here, the t-score is a test statistic. And it is our estimate, our sample mean, minus the assumed mean over the standard deviation of our estimate. So if we come back to our Excel file, let's put this over here. All right, so what that tells me is I want my sample mean minus my assumed mean over my standard deviation. So that's the number of standard deviations or standard errors I am above the mean. The degrees of freedom, over here on my handy formula sheet, I'm doing this for one mean, so my degrees of freedom is sample size minus 1, sample size minus 1. And this is a right-tailed test. Oops. This is a right-tailed test, so if I go to my formula sheet, I'm looking at this sort of situation, and my p-value is calculated by looking at the right-hand probability, so 1 minus t-distribution. I'm this many standard deviations above the mean with that for the degrees of freedom and always accumulate. So my p-value is about 2%. So with this p-value, we reject the null hypothesis. In context, that means we have sufficient evidence to believe that the true test average is greater than 69%. Notice that we do not say that it's equal to 72. We do not say that it's not 69. We just have evidence to believe that it's greater. You have to leave yourself a little bit of wiggle room here because you could be making a type 1 or a type 2 error. You don't know. All right, now to conclude this guy, we should create an estimate of the new statistics. So what we want to build now is a confidence interval. So now the confidence interval is based on our sample information. So the confidence interval is, excuse me here. So we want a 95% confidence interval. So I want the critical t-score. So this is t dot inverse of 0.975 with, where's our degrees of freedom? There's our degrees of freedom. All right, so that's how far out I want to go. My margin of error, my standard deviation now needs to be built on my sample mean, not my assumed mean. So I'm going to be saying this is the sample standard deviation over square root of sample size. Now I redo this calculation here, even though there's the exact same calculations I got there, is when you're dealing with proportions, these will actually be different from each other. My margin of error is the product of those two. And now I can build my confidence interval. So my lower bound is my mean minus my margin of error. And my upper bound is my mean plus my margin of error. Okay, now notice that I get dangerously close to that 69%. Well, that just means, okay, we rejected the null hypothesis, but it still could be darn close to 69%. So we're 95% confident that the true mean is between 69.1, give or take, and 75.5, give or take. That, of course, means that in approximately 95% of all samples created in this way, we will capture the true mean with our confidence interval. That does not say that this confidence interval actually captures the true mean. It just says we're 95% sure that it's going to. I hope this has helped for a 1SampleT test.